At in third eye, our project is a vision-based vehicle collision warning system for the rear view of bicycles. Nowadays, traffic safety has become a significant issue due to the rapid worldwide growth in the number of vehicles. In Sri Lanka, out of 13,202 road accidents last year, 96 involved bicycles. This is due to an increasing number of people taking to riding bicycles. There are many driver assistance systems that support the driver by informing on, actively assisting in, or taking over part of the driving task. A collision avoidance system is one of the driver assistance systems that helps the user by informing them about the warnings of collisions. Here we have developed a vehicle collision warning system for the bicycle's rear view. Here we are developing an improved warning system which can detect the possibility of collisions from the video captured from the rear view monocular camera on the bicycle. We are using monocular cameras as they are less expensive and readily available. We can even use our mobile phone camera. More than half of all road traffic deaths are among vulnerable road users such as pedestrians, cyclists and motorcyclists. As you can see in the graph, the worldwide death rate of bicyclists is increasing with each year. Currently, many people are going back to the bicycles not only in Sri Lanka but in other countries also. Therefore, this collision warning system may be useful to those bicyclists. If we see the majority of recently manufactured automobiles, they come with built-in advanced driver aid systems. But there are still many vehicles on the road today they lack necessary infrastructure to use these types of advanced driver assistance systems. Most modern driving assistance systems are making use of numerous inputs from numerous sensors, including camera, radar, laser, GPS, sonar, and others. To improve accuracy, most systems combined camera vision with at least one other sensor input, and some used stereo cameras rather than monocular cameras. Contrasted to stereo cameras, monocular cameras are less expensive sensors, but they lack detailed information like depth. Depth estimation using LiDAR is computationally more expensive, but the stereo cameras are not much more expensive than LiDAR in practical applications. Most people can't buy an advanced safety system for their vehicles due to their low income as it is more expensive. Therefore, the development of a cost-effective safety mechanism is crucial. And also, it is not possible to add those heavy sensors to bicycles. So we are focusing on monocular cameras because it is less expensive and compatible. The objective of our research is to synthesize state-of-the-art approaches in computer vision to detect potential vehicle collisions from monocular camera videos and generate warnings. First step is to detect vehicles in a frame and draw a tight bounding box on each vehicle. Second step is to track the moving vehicles across different frames and give them a unique ID. Third step is to predict the trajectory of vehicles using previous N frames. And the final step is to give warnings to the user based on the trajectory predictions. We propose a solution for bicycle assistant with an accurate recollision warning system which uses a monocular camera. This solution uses a computer vision techniques and pre-trained deep learning models. There are 5 main steps in this solution. The first step is to detect the vehicles in the frame, and the second step is to draw a line or 3D bounding box around those vehicles. And the third step is to track the vehicles across consecutive frames. And the fourth step is to predict the trajectory of each vehicle. And final step is to give warning based on the trajectory predictions. Here you can see the methods that we propose for this solution. The first method is using 2D bounding box, and the second method is using 3D bounding box. The first method, we feed the frames of the real-time video to the YOLO model. The YOLO model will give the vehicle detection and segmentation. This result is used to detect the extreme points of the vehicle. Then a line is drawn along the vehicle to tightly bound it. The coordinates of the line is used to predict the future trajectory of the vehicle, and it is used to trigger the warning for the user. The method 2, instead of the YOLO model, we use 3D object detection model, which will return 3D bounding box as a result. Then the coordinates of the 3D bounding box will be used to predict the future trajectory of the vehicle, and the warning will be triggered. Object detection is the task of detecting instances of objects of a certain class within an image. We are using object detection to detect vehicles in every frame. As you can see in the image, bounding boxes are drawn on each vehicle using an object detection model. Here we have planned to use YOLO for object detection. YOLO, which stands for You Only Look Once, is a state-of-the-art real-time object detection model. Object tracking is an application of deep learning where the program takes an initial set of object detections and develops a unique identification for each of the initial detections, and then tracks the detected objects as they move around frames in the video. As you can see in the video, the ID of the vehicle does not change the frame. This is achieved by using an object tracking algorithm. We use an object tracking algorithm to keep track of the trajectory of each vehicle. There are various algorithms for object tracking such as deep sort, strong sort, etc.
There are some problems with the 2D bounding box. One of the problems is estimating exact distance between vehicles from only monocular image. Data is challenging due to the lack of reliable depth information. The other problem is the 2D bounding box does not exactly bound the vehicle. It covers some non-vehicle areas. As you can see in the image, if it tracks the trajectory with only a 2D bounding box, then the non-vehicle area will be in the danger zone of the bicycle. So it will give a false warning. To overcome this issue, we have two solutions. One is the line drawing and the other one is a 3D bounding box. Line drawing. Here we are drawing a line along the border of the vehicle to differentiate the non-vehicle area. The vehicle is segmented and the segmentation mask is used to draw the line. Here we tried two different approaches to find the optimal line. One method is using the edge detection algorithm. The other one is using convection algorithm. Line drawing using edge detection. Here we use line segment detector for detecting edges. It is an algorithm that is available in OpenCV library. The LSD is an algorithm for detecting the segmenting digital images, we try to detect the sight edges between the wheels of the vehicle. The LST will detect all the line edges in the image. In this image, we can see that the algorithm detects the line between the wheels. We use two criteria to select the appropriate edge: the line with the angle of threshold and the line which has maximum distance out of those that satisfies the angle criteria. The selected line is extended to toe the border. Line drawing using convex file. The convex file of a set of point is the smallest convex polygon that contains all the points in the set. We are heading contour of the vehicle using the OpenCV library. Image 1, this is the contour of the vehicle. Then with the contours point, we are using the convex file algorithm to find the extreme points of the vehicle. Image 2, this is the convex file drawing of the vehicle. The lines will be used to draw the border. These two images are from our work. This is the final output done by us using a convex file. Here you can clearly see the line that is drawn along the border of the vehicle. Here we draw an irregular octagon. We choose 4 lines that maximize the non-vehicle area. For example, after obtaining the convex file points, we extend the consecutive points. Consider the left and bottom of the bounding box. Among the extended lines that intersect the left and bottom lines of the bounding box, we select the line that maximizes the non-vehicle area. Similarly, we choose 4 lines, then join those points with the bounding box and ultimately obtain the irregular octagon. 3D bounding box estimates the problem mentioned above by bounding the vehicle along the border. 3D bounding box estimation requires more camera calibration and additional parameters. A camera intrinsic matrix is a 3x3 matrix that describes the internal characteristics of a camera. Without this intrinsic matrix, it would be impossible to accurately project a 3D bounding box onto a 2D image. The camera calibration can be estimated using two methods. One is checkerboard method and other one is using deep learning model by Google Research. Camera calibration using checkerboard method. The camera intrinsic matrix can be estimated using checkerboard images. Here we take multiple photos of the checkerboard from different angles using camera that we need the intrinsic matrix. OpenCV library is used to estimate the camera intrinsic matrix from these images. 3D bounding boxes for images that are taken by a phone camera. The intrinsic matrix of mobile camera is estimated using the checkerboard method. Camera calibration using deep learning model. We have used the implementation of the paper depth from videos in the wild and supervised molecular depth learning from unknown cameras. The model takes 3 consecutive frames as an input and estimates the intrinsic matrix of the camera. The model does not perform well. We need to manually modify the matrix. We have used this method to get the intrinsic matrix of the videos that we took from the internet, because without camera we can't get the intrinsic matrix. That is why we use this method to estimate the intrinsic matrix for our collected videos. These are the 3D bounding boxes for a video that is taken from YouTube. The deep learning model is used to get that intrinsic matrix. Kalman filter is used for smoothing trajectory points. It helps to remove noise and irregularities from the trajectory data. The filter uses recursive algorithm to estimate the true trajectory based on measurements and a dynamic model. Kalman filter is particularly useful in situations where there are measurement errors or uncertainties in the trajectory data. By applying the Kalman filter, the trajectory points become smoother and more accurate, improving overall analysis and prediction tasks. Trajectory prediction is the process of forecasting the future path of movement of vehicle. We use two different methods for trajectory prediction: Kalman filter and polynomial regression. The collision detection system will give a warning based on severity of the collision. The warning will be triggered when the predicted trajectory of the vehicle enters the danger zone. According to the experimental results, it was indicated a warning for 4 to 8 seconds prior to a potential collision to maximize the safety. Here we have some alerting method. For the ego vehicle, the system will show the warning on the display and a warning sound will be triggered. For the vehicles, an emergency light will blinking in the back of the ego vehicle. Here some of the benefits to the bicycles. Mobile phone cameras can be used, appropriate cost, size and weight for bicycle, alerts, non-ego vehicle drivers, display notification system and bicycle motor. Experiment. We collected 3 types of data for our research. First, we captured videos using our mobile camera. Second, we collected data from the internet. Third, we utilized the Kala simulator to generate synthetic accidents and record them. It is useful because we can directly get the camera intrinsic matrix for 3D bounding box estimation. Finally, we tested a total of 60 plus minutes of videos. Here you can see the performance matrix for both of our approaches. We can see that the line drawing method outperforms the 3D bounding box method. Demo video.